For slow scan television, only still images are suitable for transmission to meet the bandwidth requirement, which is the same as single sideband, about 3 kHz. Computer software and computer sound cards are used to send and receive slow scan TV signals. SSTV requires 100% duty cycle transmissions, so reducing output power is necessary to avoid overheating the transmitter. Here is an example of an actual slow scan television image. Which of the following is the video standard used by North America fast scan ATV stations? A. PAL, B. DRM, C. Scotty, or D. NTSC? The answer is D. NTSC. What is the name of the signal component that carries color information in NTSC video? A. Is it luminance, B. chroma, C. hue, or D. spectral intensity? Answer B. Chroma. How are analog slow scan television images typically transmitted on the HF bands? A. Video is converted to equivalent baudot representation. B. Video is converted to equivalent ASCII representation. C. Varying tone frequencies represent the video are transmitted using PSK. Or D. Varying tone frequencies representing the video are transmitted using single sideband. The answer is D. Varying tone frequencies representing the video are transmitted using single sideband. Which of the following is an acceptable bandwidth for digital radio Mondale DRM based voice or slow scan television digital transmissions made on the HF amateur bands? Answer A. 3 kHz, B. 10 kHz, C. 15 kHz, or D. 20 kHz? Answer A. 3 kHz. And now let's consider receiver performance. One of the key parameters is sensitivity and noise. In particular, the minimum discernible signal, the MDS, which is the noise floor of the receiver. Now, the MDS may be reported in either dBm or microvolts. Now, sensitivity and noise. What is the MDS for a receiver with a minus 174 dBm per hertz noise floor if a 400 hertz filter is used? Well, the bandwidth ratio in dB equals 10 times the log of the bandwidth, which would be 10 times the log of 400 for this particular problem, which equals 26 dB. We then add that 26 dB to the MDS, so the MDS would be minus 174 plus 26, which equals minus 148 dBm. Suppose we change to a 2.4 kilohertz filter. The bandwidth in dB would be 10 times the log of 2400, which equals 34. Again, we add that 34 to the MDS, which would give us minus 174 plus 34, which is minus 140 dBm. But that is a theoretical MDS. The actual MDS is the theoretical MDS plus the noise figure. If we have a receiver with a minus 174 dBm per hertz and a 400 hertz bandwidth filter, what is the noise figure of 8 dB? Well, the actual MDS would be minus 174 dBm per hertz plus 10 times the log of 400 plus that 8 dB, which gives us minus 140 dBm. Roofing filters are high-performance filters that have a bandwidth wider than that of the widest signal that will be received. Their purpose is to reject as many as possible of strong adjacent signals. Although crystalline mechanical filters have historically been used for this purpose, digital signal processing DSP filters are now replacing them. DSP filters built into external speakers are very effective and have become very popular. Dynamic range refers to the ability of a receiver to tolerate strong signals outside the normal passband and still operate properly. We can state a general definition of dynamic range as the ratio between MDS and the largest input signal that does not cause audible distortion products. An input signal can be strong enough that the receiver no longer responds linearly and its gain begins to drop off. Intermodulation distortion can occur if we have two or more signals that can beat against one another. For instance, if we have one station operating on 146.52 MHz and another at 146.70 MHz, theory says we could have a distortion product at 146.34 MHz. That would come from the formula 2F1 minus F2. Second order or even third order intermodulation distortion can occur when two signals are close together in frequency. For instance, if we have one signal at 14.020 MHz and another at 14.035 MHz, we could wind up with a distortion signal at 2 times 14.02 minus 14.035 MHz, which would be 14.005 MHz. Second order IMD products can occur at the sum and the difference of the input signal frequencies and their amplitude changes 2 dB for every 1 dB of input signal change. There can also be third order IMD products. Digital frequency synthesizers in radios are becoming more and more popular. They exhibit small variations in frequency, that is, they hunt, as they adjust their frequency based on their reference clock signal. This creates phase noise, which sounds like a hiss sound that can be heard in a nearby receiver. When two stations transmit an FM signal on the same frequency, the receiving station will hear only the stronger signal with buzzing and clicks, and that is all that is left of the weaker signal. This is called the capture effect.